So this is the section 15.3, heterogeneous equilibria and manipulating with equilibrium expressions and expression using substances in a gas phase. So when we have, let's say this is a reaction, carbon dioxide gas reacts with the carbon in a solid state, forming carbon monoxide. We know that the Kc, equilibrium constant expression using concentration, equals to the concentration of the product raised to the power of the coefficient over the concentration of the reactants over their power raised to the power of their coefficient, which is 1. So this is a K with the asterisk. So, which is different than the real Kc, but we want to derive for this formula. So this substance here, this reactant, is in a solid state. And the concentration of the carbon in a solid state, it's really constant. Because recall what the concentration is. Concentration is mole over the volume, or amount over the volume. If we will take carbon solid, we will increase its amount, its volume will increase accordingly. So when we will divide mole by volume, we really will get the same number. So this is why this concentration of the C is constant like the Kc. And that's why we can derive the really correct expression for the Kc. It's a concentration of the product, which is a gas state, over the concentration of the reactant, also in a gas state. In other words, if you have equilibrium where the substances are in a different phases or state of matter, it's a heterogeneous, it's a gases, solid, liquid, aqueous solution, we will not include in the Kc expression the concentration of the substances in a solid state or liquid state. We only will include substances which are in a gas state or aqueous solution. So we are not including solids and liquids because their concentration is constant. So this is a sample problem. Write the expression for each of the following reaction. Pay attention to their state of matter. This is solid, and this is solid, and that's gas. So that means in the expression of the Kc, we're not going to include calcium oxide and the calcium carbonate because they're in a solid state. As you can see over here, this is what we have for the A. Kc just equals to the concentration of CO2 raised to the power of 1. We are not including the concentration of substances which are in a solid state. In a B, we did not include the concentration of a substance in a liquid phase. For the B, you can see Kc equals to Ag22 plus in aqueous solution over the Ag2 plus also in aqueous solution. So as you can see from here, we are excluding the substances in a solid and liquid state from the Kc expression. As you can see for the C, we only have the concentration of a hydrogen gas H2 raised to the power of 2. And for the D, the product is the liquid. Not going to include the liquid. So we just put 1 over the concentration of O2 gas, we're over the concentration of H2 gas raised to the power of 2. Now, if we have the expression for equilibrium, this is your reaction giving, and we can perfectly derive the Kc expression for this reaction, for the forward reaction, which occurs from left to right. What if we will reverse this equation? Now NO2 will react to form the NO and O2. What is the Kc for the reverse reaction? Well, we will write it down. We know it's a concentration of the products over the concentration of the reactants But if you will look at the expression, you compare K prime C with the Kc, then we'll see that the Kc equals really 1 over Kc. So it's a reciprocal of the Kc for the forward reaction. So if you're reversing a reaction, you can take 1 and divide by the value of the Kc for the forward reaction to get the Kc for the reverse reaction. What if we want to take this equation, and we want to double the amount of each substance? So instead of 2, we have 4, we have 2, and we have 4. So we can write down the expression for the reaction where the amounts were double, but it is really, you can take the Kc and you can square the value of the Kc to get the new Kc for the reaction where we double the concentrations. What if I have two reactions? This is one reaction, that's a second reaction. What if I want to add those two reactions together? Reactants together to the left side, products together to the right side. I can perfectly write Kc expression for my overall sum reaction. But it is really a product of those two Kc expression for those individual reaction. So the Kc of the first reaction times the Kc of the second reaction is the sum of those two reactions added together. So this is the equilibrium expression. How can you manipulate with that? You can use this. It's also is given to you in the textbook. You can print this out and you can use it when you will be taking an exam. And this is also is the sample problem 15.4. I assigned that to you on Alex to read the textbook. So make sure you understand how they determine the Kc for the reactions asking for. So now when we have substances, and the substances, reactants, and the products are gases. So A is a gas and B is a gas. So I can write down again Kc for this reaction. It's a product, concentration of a product raised to the power of B over the concentration of the reactant raised to the power of A. But I also can calculate the Kp for this reaction if I know their pressure at equilibrium. Pressure of the B product raised to the power of its coefficient over the pressure of the A reactant raised to the power of A. From the ideal gas law, we know that the PV equals nRT. PAV equals to NA-RT. And for the PBV equals NBRT. And if I will find the P, pressure of the A, I will have to take and divide both sides by V. And then you can see the moles over the volume. This mole over the volume is a concentration. It's the expression for the concentration. We know molarity. Molarity is mole over the volume. So then I can say that the PA equals to concentration of A multiplied by RT. R is a gas constant. And the PB equals concentration of B RT. So if I have my expression Kp, then I can write for the Pb, excuse me, for the Pa, it's a concentration of A RT. For the Pb, it's a concentration of B RT. So I will substitute for the PA, I will substitute the expression for the PA. So I'm getting the concentration of B over concentration of A. RT is a B minus A. So this is the moles. This is the mole of the B substance. This is a mole of the A substance. And really, if you want to find Kp from the Kc, so you have to take Kc and take R and T, gas constant, temperature in Kelvin, and raise it to the power of the delta N. Delta N is the moles of the product minus moles of the reactant, and then you will get value for Kp. So Kc and the Kp for the same reaction, they have a different magnitude, different values. They only will have the same value if the delta N equals to a 0. So if this is 0, so anything raised to the 0 power is 1, then the Kp equals to Kc. You can only use this equation Kp if the substances are all gases. So, and again, they're giving you sample problem. So pay attention to the sample problem, try to follow it and understand that. This is the 15.4, using equilibrium expressions to solve problems. In here, you will compare the QC, if you remember, it's called the reaction quotient, with the Kc, and see how, if they're different or if they're equal to each other. And we will predict if they are different, QC is different than the KC, we have to predict which direction, left or right, the reaction has to proceed to reach the equilibrium. Should it go to the right to make more product, and then the equilibrium will be established, or the reaction will proceed to the left back to form the reactants, and then it will establish the equilibrium. So, and then I was telling you, to determine the direction, we have to compare Q, which is the reaction quotient, has the same expression as the K. The only difference between Q and K is in the K, all the concentrations are equilibrium concentration. In a K, they are not necessarily the equilibrium concentration. They might be the concentration at any given time, not necessarily equilibrium. So when Q is less than K, and don't forget, Q is just the ratio of the product, concentration of the product over the reactant. Q is less than K, then the ratio within concentration of the products to the reactant is too small. So first of all, reaction is not at equilibrium, and to reach the equilibrium, reactants must be converted to form products. That means system has to proceed in the forward direction or from left to right to make more product. When Q is equal to K, that means the system is already at equilibrium, and those concentrations are equilibrium concentrations. So there is no net reaction in either direction. And when the Q is greater than K, then we have the ratio of a concentration of products to the reactant is too large. Reaction is not in equilibrium. To reach the equilibrium, product must be converted back to the reactants, and the system will proceed from right to left. So the Q, you can find it the QC compared with the KC, or QP compared with the KP. So they're giving you this problem. This is the reaction, and they're telling you that the equilibrium constant for this reaction is 1.2. And they're telling that at the start of a reaction, the concentration of all the substances are giving to us. They wanted to know if the system is at equilibrium. And if the system is not at equilibrium, they wanted to determine in which direction it must proceed to establish equilibrium. So what we will do, we have to write down the expression for QC, substitute all those variables with the values, and calculate QC. As you can see, QC 0.621 is less than KC, which is 1.2. And now we are in this Q is less than K. That means we do not have that much. Well, first of all, reaction is not at equilibrium. We don't have a lot of products. And in order to reach the equilibrium, the reaction has to proceed from left to right.